Welcome back to All This Math. This is Professor Parker, and on today's session, we are going to simplify some radical expressions. As you see behind me right here, we're going to simplify some radical expressions. Before I get into that, though, I'm wearing my George Washington Carver University sweatshirt, which is an ode to George Washington Carver. Shout out to George Washington Carver. Rest in peace to him. A great scientist of African descent in the United States of America who did great work at Tuskegee University down in Tuskegee, Alabama. Down there, recruited by Booker T. Washington to come into that institution and to not only teach science to the students enrolled at Tuskegee University, but one thing that I thought was dope, which is kind of the spirit of what All This Math overall as an institution is that George Washington Carver had a traveling science, basically a science laboratory on a horse and buggy, right? Where he would go out into the community and the surrounding rural areas around Tuskegee University and teach the people. He would teach the people science out in the community, basically like out in the streets, like kind of like how. And I remember that being an influence to me to develop All This Math as a YouTube channel and as an entity, because that's really where it's at. You know, you want to teach the people, that are in the schools that you currently work in, but you also want to extend your reach. And you want to be able to help other people that are not in classrooms that you're standing inside of. So shout out to George Washington Carver. And I suggest and recommend to everybody to do more research and more due diligence about George Washington Carver as well, and all of his achievements, his scientific achievements, his work, not only with the peanut, but with the soybean and other scientific achievements as well. All right. Now, as I said, we're going to simplify some radicals today. So I got two examples up here. And both of the radican is the number inside the radical sign. Here you have the radical sign. Here you have the root. The root in number one is 3, right? And the radican is 20/3. So that's a fraction. So one of the things I like to do when I'm dealing with a radican that's a fraction is I break the radican down into two separate radicals, looking like this. So now I got the cube root of 20 divided by the cube root of 3. All right. And, I do that because, I might need to rationalize, because then I check and see, okay, can I take the cube root of 20? Is 20 a perfect cube? No, 20 is not a perfect cube. There's no whole number that I can multiply by itself and then by itself again that will equal 20. And then I look in the denominator. Is 3 a perfect cube? No. There's no whole number that I can multiply by itself and by itself again where my product will be 3. All right, so we can't simplify the numerator, so that's cool. We could just leave that alone, right? But the denominator, this needs to be simplified. We got to do something with this. We need to rationalize this, because when we say simplify, we mean tighten your problem up. Tighten it up, make it nice and neat, right? So this denominator should not have a radical sign in it. Remember that. When you're simplifying expressions, if you have a radical, you should never end up with a radical sign in your denominator. And there's a way to do that. There's a way to go about simplifying and getting rid of the radical sign when it's in your denominator. What you want to do is you want to multiply this denominator. Well, actually, you're going to multiply the entire fraction, right, by the same term in the numerator and the denominator. But what you're trying to do is you're trying to get a product in your denominator that is a perfect cube. That is a perfect cube, right? So 3 is not a perfect cube. But then you got to ask yourself, like, what perfect cubes do I know of, right? And in order to get to that perfect cube, what would I have to multiply 3 by to get to that perfect cube? Now, if you don't know all the perfect cubes, well, not all of them, you don't need to know all of them, but if you don't know some of the lower level, the lower perfect cubes off your head, that's fine. Just write a list like I'm about to do. So what I would do is I would say, okay, 1 to the 3rd power, that's 1, because 1 times 1 times 1 is 1. Then I go up in numerical order. 2 to the 3rd power. That's going to be 8, not 6. A lot of people make that mistake. 2 to the 3rd power is not 6. It's 2 to the 3rd power is 8, because it's 2 times 2 times 2. That's 8. And then 3 to the 3rd power is not 9, right? It's 3 times 3 times 3, which is 27. All right? And I'm going to stop there. You know why I'm going to stop there? I mean, I don't need to know what 4 to the 3rd power is. I mean, it's 64, but I don't need to write that down. Because what I told you was we want to figure out what I can multiply by 3 in order to get a product that is a perfect cube. I can't multiply 3 by another whole number to get 1. I can't multiply 3 by another whole number to get 8. But I can multiply 3 because I know my multiplication facts. It always goes back to knowing the multiplication facts. That's the foundation of all of this. I can multiply 3 by 9 and get 27. I can multiply 3 by 9 and get 27. So this is what I'm going to do. Check this out. I'm going to multiply by a fraction that is equivalent to 1. And a fraction is equivalent to 1 when you got the same expression in your numerator as in your denominator. So watch this. And that's going to be 9. Boom. 9. All right, now let me explain this, just in case it wasn't that clear. Why am I multiplying by the cube root of 9 over the cube root of 9? Why am I doing that? I'm doing that because, like I said, I'm trying to get rid of this radical sign, right? I can't get rid of it right now because the cube 3 don't have a cube root. Well, 3 is not a perfect cube, I should say, right? It does have a cube root. Every number has a cube root, but we want this to be a whole number, all right? If I multiply by the cube root of 9, this product is going to be the cube root of 27. And the cube root of 27, since 27 is a perfect cube, is just 3, right here. But then you might be asking, well, why you got to multiply the numerator by the cube root of 9? That's a good question. You have to multiply the numerator by the same thing because that way you're not changing the value of this expression. The numbers can change, but don't change the value. This fraction right here is equivalent to 1. Because the numerator and the denominator are the exact same thing. So that means that this fraction right here is equivalent to 1. And since this fraction is equivalent to 1, that means that when we multiply this fraction by this fraction, we're not changing the value. The value stays the same. The numbers are going to change, but the value stays the same because we're multiplying by a fraction that's equivalent to 1. So we might as well just be multiplying by 1. But we're not going to multiply by 1 because if we multiply by 1, we're not going to get the number combination that we need in the denominator in order to rationalize this expression. So look what's going to happen. Because these are both cube roots, I can do 20 times 9. 20 times 9 is 180. Boom, that's my numerator. Cube root of 180. Then in the denominator, like we already discussed, the cube root of 3 times the cube root of 9 is the cube root of 27. Now, look at your numerator. Like now I'm trying to see, like, can I simplify the cube root of 180? Nah, I can't. Because even if I go, like, I already know 1 to the third is 1, 2 to the third is 8. 8 is not a factor of 180, right? 3 to the third is 27. 27 is not a factor of 180. Let me see, what's 4 to the third? 4 to the third is 64. 64 is not a factor of 180. And if I keep going up, I'm going to do 5 to the third, I'm going to get 125. I'm going to do 6 to the third, I'm going to get 216. 216 can't be a factor because it's greater than 180, right? So we can't do nothing else with this numerator. But with the denominator, we can do what I wanted, right? 3 to the third is 27. Therefore, the cube root of 27 is 3. So we got cube root 180 over 3. And that is our final answer. Now, here's one thing I wanted to make sure you don't do. Do not try to do 180 divided by 3 and get the cube root of 60. That would be wrong. You know why? Because you kind of can think of this as that these are not like terms. This is not a regular 180. This is the cube root of 180. So therefore, you can't go in there and divide it by a regular 3. All right? So keep that in mind. So this will be the final answer. Cube root of 180 over 3. Now come down here to number 2. Number 2, we're not dealing with a cube root. We're dealing with the fourth root. All right, the fourth root. Now I'm going to do my first step. I'm going to separate these two, the numerator and the denominator, into 2 separate terms. So it's going to look like this. The fourth root of 16 over the fourth root of 27. Now it just so happens that 16 is, I guess the term for this will be a perfect fourth root, right? because I know that 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So the fourth root of 16 is 2. So I can simplify the numerator into just plain 2. 27 does not have a fourth root. 27 does not have a fourth root. But we could do the same thing we did in number 1. Think to yourself, what number can I multiply by 27 so that I end up with a product that does have a fourth root, right? Or has a perfect or is a perfect fourth, I guess you could call it. 27 times what? I know 27 times 1 is 27. 27 does not have a fourth root. It's not a perfect fourth. 27 times 2 is 54. 54 does not have a perfect fourth root. 27 times 3? 27 times 3 is 81. 81 has a fourth root of 3. So watch this. That means I'm going to multiply by the fourth root of 3 on top and the fourth root of 3 on the bottom. Because that's going to create the scenario that I want. What I want is to get rid of the radical sign in the denominator. That's what I'm trying to get rid of. I'm trying to get rid of the radical sign in the denominator, and that's going to create what I want. So now in my numerator, I got 2 times the fourth root of 3. In my numerator, I should say. In my denominator, I got the fourth root of 81. And then I'm running out of space over here, so I'm going to go vertical now. So I got 2 times the fourth root of 3. And then the fourth root of 81 is just plain 3. And we good. And again, just like I warned you about in the last problem, don't try to do 3 divided by 3 get 1. You can't do that because that's not really a 3. This is a regular positive 3, right? This is the fourth root of 3. You cannot divide these two numbers. We cannot do that, all right? So I know you're going to be tempted to do it. You might see that and say, oh, well, that's a 3 and that's a 3. Let me just divide them joins out. Okay, cool. No, don't do it. You can't do that. Don't even try it. All right, resist the temptation. All right, and that's the final answer to number 2. All right, so I hope you learned something. And the key now is to go and practice some more problems like this. Do 100 problems, just like these. That's how you master anything in math. Do 100 problems. Learn a new skill, and then go do 100 problems. That's how you get it done. And also, if you have not subscribed to the All This Math YouTube channel, please subscribe to the channel. Go ahead, hit that button. Also, turn on the post notifications so you'll get notified whenever I put up new content like this. And share this video. Share this video. Tell somebody about it. All right? And always remember, there's all this math all around you. Peace.